All right, welcome to this video. We're going to talk about Gibbs Free Energy. What is it? How do you calculate it? Help for our students here at Andrews University and whoever else is watching this. I'm Dr. Ryan Hayes, professor of chemistry at Andrews University. Let's get started. What is Gibbs Free Energy? It is based on the second law of thermodynamics and has separate talk about what that is all involved with. And the gentleman who did this calculation and coined the terms, his name is J. William Gibbs, and you can see his lifespan, 1839 to 1903. Second law of thermodynamics says that for a reaction to take place, it has to be spontaneous and will increase the entropy of the universe. So we looked at the surrounding entropy, the entropy of the system. But remember, if you go back and you look at the entropy of the universe video, we can understand that we can replace the surrounding entropy with the negative enthalpy divided by temperature. Now, this was a good starting point to create a different way of looking at the entropy of the universe. By multiplying by negative T through each term, J. William Gibbs came up with a new equation that actually we use more often than the equation with the S's in it. And so you get this new set of equations, symbols here. Negative T delta S of the universe is equal to the enthalpy of the system minus the temperature times the entropy of the system. Then negative delta T times the entropy of the universe was replaced with a new symbol just called delta G for Gibbs. So now we're going to be using this delta G term instead of the delta S of the universe. A couple important changes in this new equation here that we need to think about. But here is the Gibbs free energy equation. And there's some great things that we learn from this that we may not have gotten from the other iteration of the second law of thermodynamics. And so we get that the Gibbs free energy of a chemical reaction, which is related to the entropy of the universe, is equal to the enthalpy of the system minus the temperature times the entropy. So where does the term free energy come from? Well, it really comes from the idea that enthalpy provides a bunch of energy for the chemical reaction, and then there is a correction for the entropy. Now, sometimes the entropy can add energy, sometimes it can overcome endothermic reactions, sometimes it hurts. And so Gibbs is this, what's remaining, what's free, what's available after you correct the enthalpy and the entropy and the temperature together. So here's a question I like to ask my students, and you can think about that as well. Can the temperature, capital T here, ever be negative in this calculation? Give you a moment to think about it. What do you think? Yes, no, sometimes yes, sometimes no. The answer is B, no. Temperature is in Kelvin. It's always in Kelvin. In chemistry, we really don't do anything in Celsius or Fahrenheit, sometimes in Celsius, but it's really stuff that we should be doing in Kelvin. Kelvin is lowest value is 0 and never gets into the negative numbers, and we won't get into some of the experimental science out there, but in general, 0 is the lowest number. It's never negative, okay? So that's important because that means it'll never like flip the sign in there because we have this negative T delta S. We don't have to worry about temperature doing that. Now, this is what my students picked. This is now basically 2/3 of the way through second semester of general chemistry, and they still didn't quite understand that, but at least half of them did. All right, now what can we do and how do we think through this equation? So Gibbs free energy change then is the total energy of your chemical reaction, your system that's available for doing chemical work. So now, if you have an exothermic reaction, we know we have a negative delta H. If you have a system that's spreading out, so you have a positive delta S, you're going to get a negative T times that positive delta S, and overall delta G will be negative at any temperature because you got a negative delta H and a positive delta S. And so the whole negative T delta S term just stays negative. And so that means, and this is the most favorable chemical reaction, an exothermic one that's producing energy. And then you get a system that maybe is spreading out. Those are spontaneous chemical reactions. And so we say those are product favored. You're going to make lots of product. Chemical reaction is going to go. It's spontaneous. You might need a spark, might need some activation energy, but that reaction is favored and wants to go. Now, the complete opposite of that is for an endothermic reaction, a positive delta H, and then a reaction that's coming together. So we would say the entropy is decreasing in the system, and that would make a negative delta S. What that does, though, it gives you an overall positive Gibbs free energy, a positive delta G, because we have a positive H, and then you're going to minus the temperature times a negative delta S. So that's going to turn that whole term into a positive number. This is the worst case scenario. We would say this is not spontaneous. You're going to typically end up with reactants. Very little products are going to get made. Does this mean the reaction doesn't go? Basically, no, it doesn't really want to go. I mean, you're going to get a little bit, but it's not efficient. It wants to stay as reactants. There's some things we can do with Le Chatelier's principle and some knowledge. And if you work outside the system, you can probably create a way to make that reaction go. But it's going to be very hard to do. Okay, now, if we think about it, there are 4 options for chemical reactions in terms of signs of delta H and delta S, your enthalpy and your entropy. The first one that we just sort of talked about, the most favorable situation is when you have a positive entropy and a negative enthalpy. Doesn't matter what temperature it is, it's always going to be spontaneous. It's green, it's good to go. Your second favorable option, I guess you would say, that to create spontaneous chemical reactions, this one's temperature dependent. So when you have a positive enthalpy, and that's an endothermic reaction, but you have a positive entropy, that's a very favorable. So if your temperature's high enough, that'll overcome the enthalpy, and you're going to get a negative delta G. There's another temperature-related situation is for chemical reactions that are exothermic, but they're coming together, so they have a negative entropy. At low temperatures, these are favorable. The delta G is negative, so that'll go. Then there are the least favorable chemical reactions that we already talked about when you have a positive enthalpy, so it's an endothermic reaction with a system that's contracting a negative entropy. Now, quadrant A, B, C, or D, which one best represents a phase transition, like going from solid to liquid or liquid to gas? Call that a forward transition. I'll pause a moment so you can think about it. All right, hopefully you answered B. B is the correct one. Why? Because as you are putting energy into the system to make, say, a liquid boil or solid melt into a liquid, put energy in, that's endothermic. And if it's going from a solid to a liquid or a liquid to a gas, those are always spreading out. So that's a positive entropy. Now the reverse of that, when you're doing a phase transition from a gas to liquid, liquid to solid, then that would fall under quadrant C, okay? Now here is what our students answered in previous years. They didn't really know it was A or B. Previous year, I think it was 2017. And then we can see here that this, just this year, we did this. And most of the students got it correct, so that's good. All right, there's 2 ways to determine and calculate delta G. We've seen one already, but there is a second way to figure out the free energy for a chemical reaction. So we've looked at the first one already, where if you know what the enthalpy is and the entropy, you can plug those in with the temperature, and you can figure out what you need, what you will get in terms of the free energy. There is a second way that could be a little bit quicker to get the free energy of a chemical reaction. That's to use tables of Gibbs free energy of formation. So there's a very similar equation that we've used for enthalpy and for entropy of a chemical reaction. And it's where you sum up the Gibbs free energy formation for the products minus the sum of the free energy of formation of the reactants. There's tables of these. They're given in our textbook and online homework. They often have tables there, and you can just look up these values. They're in kilojoules per mole. They're very similar to enthalpy numbers. You will see that elements in their standard state are 0. This is the exact same thing for enthalpy of elements. So here's another table that they typically come with the enthalpy of formation, and then Gibbs free energy, and then entropy. Notice the units, the unit changes. These are very important. So I've got a list here. It's often helpful to remember what are the elements in their standard state. And so for oxygen, hydrogen, nitrogen, fluorine, chlorine, bromine, iodine, they're all diatomics. Most of them are gases except for bromine and carbon. All bromine and iodine, they're liquids and solids respectively. And then a number of things on the periodic table are just solids, just written with their symbol. And some other examples there to look at. Of course, mercury is a liquid. So we can go and calculate the free energy of a chemical reaction just by giving the reactants and the products what their states are. We can go look up these numbers. Let's say you're going to burn some graphite, and you're going to do that in presence of some oxygen and see if you can make CO2. This is a combustion reaction. We can go find the Gibbs free energy of our product, CO2, and subtract off the graphite free energy and the oxygen free energy. Gibbs free energy there. Well, it turns out when we go look it up that we find 0 for the 2 reactants because these are elements in their standard state. So this makes it a lot easier. And then we have our Gibbs free energy of the product, and that's going to turn out to be the Gibbs free energy for the entire chemical reaction. All right, so that's a pretty easy way to calculate it. And we can see that with it being a negative number, and it's pretty large in terms of energy, kilojoules, that this is a spontaneous chemical reaction. Just needs to be negative, and that's how we know it's spontaneous. This is a product-favored reaction, so the reaction is going to end up making a lot of products, going to be high concentration. This is combustion reaction. It does go. We can prove that with the delta G. Now, what's easy about this, it's pretty easy to plug in the numbers and get your sign. However, you cannot tell the temperature dependence with this type of chemical equation here to calculate free energy. All right, what about combustion of acetylene? Let's look at another example. You could go and look up the free energies, the enthalpy of the chemical reaction using the summation, and I went ahead and did that already. Because sometimes you're just given the enthalpy for the chemical reaction. That's what the little r can help you to understand. And then I've already calculated the entropy for this chemical reaction, and I got a negative 97.4 joules per Kelvin. I'm going to divide by 1,000 to switch it into kilojoules. That way my 2 energy terms here are in the same units. Now using the second law of thermodynamics, the Gibbs free energy version, delta H minus T delta S, I can plug in the 2 numbers in kilojoules multiplied by the temperature. And you should see if you should get the same numbers here. So I get a negative 1209 kilojoules. Now what's interesting is you can see that the enthalpy was a negative 1238 kilojoules, in that the entropy just sort of modified it a little bit and took away some of the energy. So it was started to head towards a more positive number. So we could still say this is our product favored chemical reaction in spite of the negative delta S. Well, how do we know it's negative delta S? Well, I got you the number. But if you look at the chemical reaction, I had 1 mole of acetylene and 5/5 moles. So that's 2.5 moles of oxygens, 3.5 moles altogether. And this comes together to make 3 moles. So you're combining a little bit, it's compressing the system. You're taking 3.5 moles, now you're getting 3 moles. So that's probably where the negative entropy comes from. So this entropy is trying to force this away, but it's such a small amount that the enthalpy easily overcomes this. So that means the enthalpy drives this chemical reaction. We say it's enthalpy driven. It's the term that makes delta G negative, because entropy was fighting this. So what does it mean to be enthalpy driven? Because some reactions are, as we've seen. Some are entropy driven. Well, it really is which term, the H, the delta H or the T delta S, which part of that equation contributes to the delta G to make it negative. Now, if they're both contribute, well, then it's neither. But in this case, like we saw before, it was the delta H that was the negative term that really made it negative, and then the entropy was actually fighting it. So we want to look at that in our examples when we go through them. Now, there are temperature-dependent chemical reactions, like back in that quadrants B and C. How could we find when they switch from being spontaneous to non-spontaneous? Well, we can use that Gibbs free energy equation, setting delta G equal to 0, and solve for the temperature. So this is a nice thing to do, and I actually did that for the chemical reaction that we just were looking at. And you can see my little chicken scratching in here. We had previously a negative 1238 kilojoules. And if we divide it by the entropy, so the enthalpy divided by the entropy will let us know what the temperature is. And it's 12,710 Kelvin. This is temperature at which the reaction becomes non-spontaneous. And that's always good to think about. Why is it above that temperature? Well, we're in quadrant, let's see, if you're in negative enthalpy, negative entropy, you're in that bottom quadrant. So that means the colder temperatures below that is when it's spontaneous. You get above that, the entropy becomes too large, and it will stop the chemical reaction. All right, here's some practice questions that you may encounter to help think through chemical reactions and Gibbs free energy and enthalpy and entropy. So it's good practice. So without doing any calculations, match the following thermodynamic properties with their appropriate numerical sign of the following exothermic reaction. Well, right away, if it's exothermic, we're going to know that delta H is negative. Let's see. Is it 1, 2, 3, or what it's going on? Well, if it's exothermic, then delta H has got to be negative. That's less than 0. Okay, now what's the entropy? Well, it didn't say anything about the entropy. I could go calculate it, but it says don't do any calculations. So what am I supposed to do? Well, we can do a tiny, like a calculation. I'm going to look at the phases. As I'm going from the reactant to the product, I see that I've got gases going to gases, so that's not going to help. But I have 4 moles of ammonia and 5 moles of oxygen here. Ooh, that's 9 moles of reactants, and it's going to make 10 moles of products. Well, that's very interesting. So that means this thing's kind of spreading out, 9 moles to 10. Not a lot, but it's a change, it's spreading out. So I would say this is going to be a positive, or this will be number 1 here, delta S. So that's how you think through it. Phase changes and number of moles. Now, what would the Gibbs free energy? I have a exothermic reaction and it's spreading out. This is quadrant 1 for me. This is at all temperatures, delta G is going to be negative. So that would be 2. He's going to be less than 0. What about the entropy of the universe? Well, it's just opposite in sign of Gibbs free energy. So it's going to have the opposite thing. So that would just be positive then. So that's in the increasing entropy that takes place there. Good things to think about there. Let's go on to another practice problem. Oops, man, I got the answer already popped up there. Okay, it's the same sort of thing. Let's take a look at, let's see, you're given a chemical reaction, the enthalpy and the entropy. Under standard conditions, this reaction would be product favored when? Well, all you have to do is look at the signs here and the sign. So we've got a positive, positive. This puts it in quadrant 2, which at relatively high temperatures, the chemical reaction becomes spontaneous. So this is practice looking at the signs of the enthalpy and entropy. Or you may get a chemical or a problem that looks like this. We're getting a chemical reaction and the enthalpy and the entropy are given. It says delta G would be less than 0 at which temperatures? Well, I can go back to setting delta G equals to 0 and solve for delta H divided by delta S, making sure that they're in the same units. In this case, I multiplied the enthalpy by 1,000 to get to joules. Taking the enthalpy divided by the entropy, I get the temperature 451 Kelvin. So This is the temperature at which it's becoming spontaneous or non-spontaneous. But then I have to think about, well, is it above this temperature or is it below this temperature? Well, noting that I have an exothermic reaction and a negative or contracting system, these are the ones that they are going to work when they're colder. This is in quadrant C, I think, if I recall. So those reactions become spontaneous or negative delta G's below the temperature that's there. All right, that we calculate. So there's 4 types of chemical reactions. They can be exothermic or endothermic, or they can be a positive entropy or negative entropy, a system that's spreading out, positive entropy or negative coming together. And we're always trying to see, does our chemical reaction fall under one of these 4 categories? Okay, so it's always great when you can get the enthalpy and the entropy, and then you can figure out where you fall in that system there. So in summary, what did we learn? We learned that Gibbs free energy is delta G. It's related to the second law of thermodynamics, except for it has a sign flip in there. So if delta G is negative, we have a spontaneous product-favored chemical reaction, and that thing wants to go and make products. There's a temperature dependence that we can calculate. So we can calculate delta G, 2 different methods. One of them gives us the temperature dependence. One just tells us whether it's spontaneous or not. So can non-spontaneous chemical reactions go? Yes, but they're going to need some help, typically outside the system. So a lot more to think about when it comes to Gibbs free energy, but this is what scientists use when we think about the spontaneity of chemical reaction is Gibbs free energy. It's what I used in graduate school to help predict some spontaneous or non-spontaneous chemical reactions. And it's the tool that scientists use. I hope you learned a few things about Gibbs free energy and that you can start using it now to solve some of your problems.